So welcome to the first day of Math 245 for the summer. And the way it's going to work is I'm going to present material. I will do examples when they're appropriate, and I'll give you a lot of explanation, a lot of development. Today is mainly vocabulary and very, very simple concepts to get used to. But there's a lot of terminology you may be completely unfamiliar with. There's other things that you may have seen in other classes, which is extremely helpful. Those who have had statistics, for example, there's a lot of overlap in this class. We take a lot of the concepts that you learned in statistics and we expand on them, particularly the probability and combinatorics aspects, permutations, combinations, things like that. That's at the end of the course. But there's other parts of the course, some of the set theory that we do in statistics that we go to in here. Now, just to make sure you understand, statistics is the lowest level math class in the United States that is transferable. There is no class that is lower that any four-year university will transfer because the prerequisite for statistics is remedial algebra. The other lowest math course that's transferable is pre-calculus, and that's only transferable to some institutions. UCSD, for example, does not accept pre-calculus. So at many schools, Calc 1 is the lowest transferable math course, but at all schools, statistics is transferable. This class is considered basically above calculus in a sense. Although the prerequisite is calculus 2, and I want to make this really clear because everybody's probably wondering why the heck calculus 2 is a prereq. There is absolutely no calculus in this class. There is no algebra in this class. So why is calculus a prerequisite? The state decided a long time ago that they want students to demonstrate what's called mathematical maturity. They want you to be able to think. And so this class is a higher level of thinking. And so that's why the calc prereq. I have no problem with admitting people who haven't even had calculus. The problem is in the last year or two, my chair and my dean have refused to sign off. So if you had Calc 1 and you want to take this class, I don't have a problem with that, but they won't sign off on it. So therefore the answer is no now when you ask the question, unfortunately, unless you can convince them, because I'll take anybody who wants to take this course. I describe discrete math as fun math for people who are math nerds. In other words, this isn't any fun if you don't like math, but if you like math, you tend to have a good time in this class because again, it's not calculus. It's not even like calculus. Now, who should be taking this class? Well, basically, if you're a math major, absolutely, you should be taking this class. If you're a computer scientist, I've heard arguments this is the most important class. Well, certainly for a lower division class. But the two most important classes, if you're a computer scientist or a math major, the two single most important lower division classes are this class and linear algebra. Because as you go further in mathematics, you don't ever do calculus again, except in upper level statistics. All of statistics is calculus based. Other than that, you basically never do calculus again. Calculus mainly is for engineers. Now, will engineers take this course? A few of them will. But most engineers don't take discrete, they don't really need to. Computer scientists need it because of the logic that you're going to be learning. You're not going to be learning programming, but the programming logic. And then the upper division version of this class is usually a requirement for computer science folk, just like the upper division linear algebra is as well. Now, we don't do any linear algebra in this class, but those two classes together, see, I'm a math guy, but I'm also a statistics guy. This class and linear are pretty much foundational for almost every upper division math class you would take if you were a math major. Again, you don't do calculus at the upper level. Calculus to a math major is kind of like what algebra is to a calculus student. It's just the basics of how to calculate things, but you don't calculate later. It's mostly theory and development. So let's start with some really, really basic stuff, vocab. And this is the kind of vocab we're going to use every single day. So I'm going to start with what's called the universal qualifier. Or quantifier, both universal. Now, our textbook likes to use the term quantifier. Other textbooks will use the term qualifier. It actually means the same thing in this context. The universal quantifier is a statement or a symbol that says this is true every time for every conceivable case. And so the universal quantifier is the term for all or for every. And the symbol, strangely enough, it's the upside down capital A. Now in calculus 1, when you wrote an epsilon delta proof, okay, if you remember doing that in calc 1, all epsilon delta proofs start the same way. For all or for every epsilon greater than 0, and then you start with the next statement. I like the symbol because math people are really, really lazy. We like symbolic notation because symbolic notation is just less writing to say the same thing. But whenever you use this symbol, you're saying it is always the case. So for example, okay, I'll give you a simple statement. Okay, in English, this says, for every real number, its square is non-negative. That's the absolute direct translation of that statement. This is going to be every day for everybody in this class. For all x element of the set of real numbers, that's a script R, x squared is greater than or equal to 0. Now, it's not a question of it whether this is true or false. It's true. The question is, how do I make a mathematical statement using symbolic notation? So over the course of things, we're going to learn all the ways of using symbolic notation. Please make sure you're muted because you're going to come up on my screen as soon as somebody unmutes themselves, they become the picture to everybody else. So for all. Now, if something isn't always the case, then don't use the universal qualifier. So a weaker qualifier is something called the existential qualifier. Again, please mute yourself. There's somebody who's extremely loud in the background, and it takes too long for me to undo everything, figure out who you are, mute you, and then come back. That's like 3 wasted minutes. So the existential quantifier is at least once, or we say there exists. Most of the time we use the term there exists, but a lot of folks don't know what does that mean numerically. When you say there exists, you know, a case where the following thing's happening, what you're saying is there's something that happens at least one time. It could happen exactly one time. It could happen infinitely many times. In fact, it could happen every time, but there exists guarantees at least one occurrence of something. And the symbol we use for the existential quantifier is the backwards capital E. Now, many of you have seen these, and maybe in your math classes, your professors use those in their lecture. I use these in every class, but I introduce what they mean early on. So there would be a situation like this, for example. There exists a real number such that 2x equals 4. Okay, that's kind of a boring statement. There is a real number out there where 2 times that real number equals 4. We all agree with that. You say, yeah, x equal 2 would be a perfect example of the truth of this. I'm not saying every real number 2x equals 4. Oh, no, that would not be true. I'm saying there's at least once. At least one time this is a true statement. So the for all and there exists become part of our everyday language because after a while, we're not only going to use those to take words and translate them into symbols, we're going to take the symbols, translate them into words, and then we're going to do the basic logic of these. We're going to look on this stuff next, converses, inverses, contrapositives, how to negate a statement. And these are all very powerful logic things. So this is the start. These are the first terms I want to introduce. So the symbol for all and there exists. Those are called the quantifiers or the qualifiers. So if you have a universal statement, then you're actually saying something. For all people in this class, or there exists at least one person in this class, right? That would be a statement. Okay, now I want to get into some of the notation of sets because what we just did there is pretty simple and pretty easy to work around. Now in sets, if I talk about a set, let me keep it real simple. You know, I have the set 1, 2, 3, 4. Now the first thing is I have another set 4, 3, 2, 1. I'll call this set A and this set B. Now equality in sets is kind of ambiguous at first because the equal symbol, okay, that's quantitative. The equal symbol generally means there's a numerical representation of something. So if I was solving an algebraic problem and I said x equals 3, then I'm saying x and 3 are exactly the same value. You don't, in geometry, if I said this shape is identical to this shape, we don't use equal, we use congruent. Right? 2 shapes being identical, there's no equal sign because there's no numerical values. Now I can say the area of shape A is equal to the area of shape B. That makes sense because area is a numerical quantity. So generally, when you use an equal sign, it's because there's a numerical quantity involved. With sets, it's a little different how we define equal. I'm saying A is this set. A isn't a number. Okay, if I said how many things are in the set, that's a totally different thing. I'm saying set A is this set. Set B is this set. Are A and B the same sets, or are they different? If you've had Calc 2, this is really confusing, because in Calc 2, a lot of the textbooks use terrible, terrible notation. Okay, does anybody want to try it? Equal or not equal? Just holler out. What do you think?
Not equal.
Anybody else?
I said they're equal.
Oh, good. I need conflict here. Okay, we're gonna have an arm wrestling match later to determine. It turns out, here's why I said this is confusing. In calculus, you learn something called a sequence. 1, 2, 3, 4 is a sequence, and here's why it's important. If I said I'm thinking of a sequence automatically is infinite, by the way. There's no such thing as a finite sequence. That'd like be saying a finite set of real numbers. No. That's totally different. That would be something called a subset of a sequence. The sequence is infinite. There's a starting point, it goes forever. If I said 1, 2, 3, 4, all of you could tell me the next value in that sequence, pretty sure we'd all agree it's 5. If I said 4, 3, 2, 1, what's the next value in that sequence? Anybody? I think it's kind of obvious.
0.
0. But a sequence, the order is everything. In a set, and here's the big difference, in a set, there is no order implied. And I want to make sure this is really clear, because this is the smartest people I teach get confused on this, because they always think sequence and set, because many calculus books will use set notation to describe a sequence. And by the way, that is absolutely incorrect. I won't use that calculus book, because it means the author doesn't even understand the most basic premise of a sequence. A sequence is an infinite ordered list. A set is just a collection of things. So if I said, for example, let me bring up the class roster. Okay, there's 40 something names on that class roster. They're in alphabetical order out of convenience, but I could have put them in order of tallest to shortest, oldest to youngest, most units to least units. There's any way you want it, best looking to, no, that'd probably be unfair, too subjective. But I could have put, or I could just say, just randomly give me a set of names. But having them in alphabetical order is convenience, because then it makes it easier to find somebody. But if I rearrange the names on my roster, that doesn't make it a different roster. It's still the same roster. The roster is the collection of names, regardless of what order I present them in. A set is a collection of elements. And generally, when we're working with sets, our sets are going to be finite, because there's a lot of things we're going to do with them. But a set is simply a collection of elements. Each thing in the set, the 1, the 2, the 3, and the 4 are all called elements. So if it's a collection of elements, then the order I present the elements cannot change the collection that I'm using. So it turns out these sets are in fact equal. If I thought of these as sequences, they would not be equal. But so how do I distinguish? It's actually the notation. I'm using set notation, which means it cannot be considered a sequence. That would be incorrect notation. And at the very least, it would be extremely ambiguous. We will never do that in this class. There's no way we're ever going to put ourselves in a situation where a person who understands what's going on could still misinterpret it, because we use notation that could be interpreted 2 ways. So as sets go, these sets are in fact equal, because they are the same collection of elements. In fact, if I said my elements are the numbers 1, 2, 3, and 4, now I'm going to jump into the future. Some of you know the answer from other classes. Does anybody know exactly how many representations of this set there are? I'm just curious, because we're going to learn that much later in the course, but some of you learned this maybe in stats, or even in basic algebra. You should have learned the calculation probably in intermediate algebra. Anybody want to guess? How many ways could I represent this set?
Is it 4 factorial?
4 factorial.
24.
24. 1, 2, 3, 4. 1, 3, 2, 4. Keep going. 4, 3, 2, 1. 4, 1, 2, 3. There's exactly 24 ways I could say the same set. This is why when we're writing a set, we usually like to have some sort of organization. For example, the class roster in alphabetical order just makes it a little bit easier to look at. It doesn't change the set. Now, the number 1 is an element. And so the symbol I would use is, I'd say 1 is an element. Now that's the symbol for element. And a lot of folks get confused. This symbol doesn't change from one context to the next. 1 is an element of set A. Okay, now I'm going to take 2 of the numbers from set A. That is not an element, that's another set, but it's a smaller set. We would say this is a subset. So this symbol means element. This symbol means subset. An element is an individual character in the set. In other words, the number 1 is an element. This is not an element. First of all, there's 2 things, but it's also an entire set. This is a set that is a subset of this set. A subset just means a smaller version of that set, a collection of things that are in that set. A subset could be all the way up to the set itself. So in a sense, I like people, when you're thinking of subset, if you thought about it in numerical terms, is there an algebraic symbol that you can kind of compare this to? Anybody want to try? It should be really obvious. What algebraic symbol does this kind of compare to? If I was talking about numbers.
Less than or equal?
Less than or equal is the perfect analogy. Oh, okay. My number is 10. Now, any number that's smaller than 10, we'd say is less than 10. But we can get all the way up to 10. Okay, so less than or equal to 10. So all real numbers up to and including 10 would be less than or equal to 10. All elements of this set, all subsets. I could have 1, I could have 1, 2, I could have 1, 2, 3. I could have 1, 2, 3, 4. All of them up to the entire set A can be a subset of A. So that's what that actually really refers to. It's like a less than or equal symbol. Okay. Now, where it is confusing is some textbooks will actually distinguish this symbol and this symbol. I don't like that because it's unnecessary. Well, many textbooks who do set theory will say, this is what is called a proper subset. That means it absolutely has to be a smaller subset. But then we exclude the possibility of the whole set, which actually from a theoretical and from an algebraic standpoint really messes things up. We're never going to do this. We're never going to say something has to be a smaller subset because there's actually no mathematics for that, because the algebra and the conclusions that we're going to make along the way, no, we want to allow for the entire set to be a subset. It's just there's too many weirdnesses that are created. So the symbol means that this is a part of this. So having said that, I don't need B anymore. Having said that, true or false?
True.
True.
False.
Oh,
False.
true.
So
That one's
true or
true.
false?
False.
False. Oh,
False.
yeah. This is an element. This is an entire set. Oh my God, that's nitpicking. No. It's apples and oranges. If I tell you one element of the set, and the number 3 is an element. This is one of the subsets of A, just like this is one of the subsets of A. Oh, okay, so that's a totally different. So if I asked you to list all of the subsets of A, you could do this. And this is, by the way, a good exercise. This is part of what we're doing. If I said, let's list all of the subsets of A, let's start real simple. Let's list the subsets that have one element. Everybody agree? Those would all be subsets. Now, what about one more? Okay, good. 3 and 4 kind of squished in there. All right, those are all the subsets that have 2 elements. Now, how many subsets have 3 elements? Well, there's 1, 2, 3. There's 1, 2, 4. There's 1, 3, 4. And there's 2, 3, 4. And there's one more. Have I listed all of the subsets of A? Have I listed all of them? Wink, wink, nudge, nudge. Wait, what else would there be? I decided to pick one element. I decided to
it
pick
an
two elements.
set?
I decided to pick three elements. What if I decide that I don't want to pick any
Is it
element?
an empty set? Oh, okay. I was just about to say that.
Perfect. The empty set is a possible subset. Now, that's the one that nobody ever thinks of. The two that people tend not to think of is the set with nothing in it and the set with everything in it. Okay, these are all the possible subsets of A. How many are there?
Two to the fourth.
Yeah. Yeah. So some of you are counting them. That's fine. There's 1 and there's 4 and there's 6 and there's 4 and there's 1. Wait, I've seen that sequence of numbers before. 1, 4, 6, 4, 1. I know that comes from somewhere. That's going to be really important later. You know, Pascal's triangle, that kind of thing. That's not an accident. There's 2 to the 4th. And here's an easy way to think about it, because this is the type of math we do in this class. Every element is either in the subset or it is not. So if I said, let's flip a coin, this is a fun one. Let's flip a coin 4 times and let's write down the sequence of trues and false, or excuse me, of tails and heads. You know, you say, well, I could have, tail, 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 head. If I said, how many ways can I do that? It turns out it's 2 to the 4th, because each choice is, I have 2 for each position. Every element is either in the subset or it is not. And I have 2 choices for each element. That's why there's 2 to the 4th. So what I've listed to you are all of the possible subsets of A, and there were exactly 2 to the 4th. There are 4 elements. This is an absolute. This is a formula. So if a set has n elements, then there are exactly 2 to the n possible subsets. But all of the subsets I've just listed. So therefore, if I chose something that either did not have the set notation, if it doesn't have the set brackets, then it's not a set. That's the only way we indicate sets in this case. Or if I gave you a set with different elements, maybe I gave you a set with the number 5 in it, then that would not be a subset of A. That's why when I asked the question, is 1 a subset of A? The answer is no, because this is not a set. This is an individual element. This is the set that contains only the number 1. They're different animals altogether. Oh my goodness. Now, that's not meant to be confusing. That's meant so that we have an absolute black and white definition that can't possibly be misinterpreted. So the lack of brackets would mean it's not a set, first of all. Now, how about if I ask the following question? I think I asked this one already. True or false?
False.
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 There were a lot of false. Yeah, it's false, but why? Because that's a set. There are no sets in this set. There are only individual elements. Can I actually have sets within a set? Yeah. Oh my goodness. Let me do the following. Should I erase them? Okay, pretend all of them are still up here. All right. Sorry. Actually, I don't need to pretend. My writing's getting awful. Okay, now check this out. Big set notation, big set notation. I have a set where one of the elements of my set is the empty set. The next element of my set is the set that only includes the number 1. The next element, and so on. I've made the elements of my big set here, I've made the elements individual sets. That's crazy. No, that's actually considered the most important set of all. This is called the power set. It's trivial. How many elements are in the power set? You said before, 2 to the 4th. Oh, so the power set is now the set of every possible subset, which is crazy. So let's call the power set, for lack of a better name, let's call this big P. This is, and by the way, how do I say something is false? It's real easy. Like that. It means it's not true. But is the following statement, is that true?
Yes.
Yes. A set can be an element. A set is an element of its power set. But a set cannot be an element of just another set of elements. There's no little sets within this set. That's why that is a false statement. Again, the notation is very important, so there's no ambiguity, so that we all agree that everything is absolute. Okay, that we kind of need that. There can't be gray areas when we're defining stuff. So the notation of is something an element or something a subset, I want that to be automatic. I want that to be trivial. I don't want that to be difficult at all. So now we're going to get to the first operation. And this is a very important operation that we will use off and on all semester. Okay, and that's what's called a Cartesian product. Okay, Cartesian product. You guys have heard that term, Cartesian something. Where have you heard that before? Cartesian.
Graph.
Cartesian coordinates.
Yeah, something XY plane. We call that generally Cartesian coordinates or a Cartesian plane or Cartesian graph. People from Cartesia obviously use that, right? Does anybody know where the Cartesian, where that comes from? It's important to me because it's one of my favorite people. It's a person. Does anybody know?
Descartes.
Descartes. That was French, you know. Descartes was an interesting character. If you study mathematics long enough, Descartes is one of the most important mathematicians. He's not my favorite. Gauss is my favorite, but Descartes is one of the most important mathematicians. But he was a scary double. Has anybody ever had philosophy? Just yell at it. Has anybody ever had a college philosophy course?
Yeah, I had 2 semesters of it.
Yeah. What else is Descartes well known for? He's not only one of the most important mathematicians that ever lived. Depending on your professor in philosophy, he was the most important philosopher. Now talk about a scary double. Math and philosophy. Yeah. Back in the day, now I don't believe any aspect of this is true, but this is what they taught me when I was in college. There was a period of human history where people questioned reality and their own existence. You know, is the table real? Are you real? Am I real? You know, they would tell you in a philosophy class that people actually questioned this for many, many years. I think it was a bunch of drunk philosophers sitting around just, you know, having fun and screwing around. But Descartes came along and said, I am self-aware, right? That I am a sentient being. That proves that I exist. And it's summarized. This is not what he said, but it's summarized in one, maybe the most famous philosophical expression. Does anybody know what it is?
I think, therefore I am.
I think, therefore I am. He basically said the fact that I can think proves that I exist. And the way they would explain in philosophy is at that moment, the argument was over. It was dead. It never came up again. I'm not really sure it ever came up in the first place, but who cares? But Descartes is this important philosopher. He's this important mathematician. And anything in algebra that involved graphing and, you know, XY plane and stuff, you're saying, but that's so trivial. But it goes way beyond that. But a Cartesian product actually is how we get our entire coordinate system in algebra. That's just a version. That's a small subset of the bigger concept of Cartesian product. So I'm going to define Cartesian product, and then you'll see where it applies to graphing in general. We do not graph in this class. No. But we should understand the mathematics because we will discuss functions and things like that. So if I said set A is, let's say, 1, 2, 3, and let's set B is not A, B. Let's say alpha and beta. Sorry. Then we define the Cartesian product of A and B. Now I'm going to introduce a symbol that some of you may or may not be familiar with. And again, it's a context thing. When giving a definition of something, 3 bars. Now, for most people in a discrete math course, I assume you've had a year of calculus at the very least. There are 2 instances where you should have seen this symbol, even if your instructors never really used it, but they've given you demonstrations. I'm going to give you 2 simple ways to remember where this comes from. Okay. Okay, unit circle. Can you calculate the cosine of theta? No. The cosine of theta is defined to be x. The sine of theta is defined to be y. That can't be calculated. That's their definition. The x coordinate is defined to be the cosine. That's what the cosine is. It's that x coordinate. Oh, and then the tangent of theta is defined to be y over x. But y over x happens to equal sine over cosine. That's an equal sign. This is the definition of the tangent function. This is a result of the definition of the tangent function. That's why we put an equal sign. It's a consequence of what I've already accepted to be true. And then I can define the remaining trig functions. When I have the unit circle and I, say I have this xy coordinate, whatever that theta is, cos theta is defined to be the x. That's it. That's where all of the basis of trig comes from. I would hope that this is the first 5 minutes of everybody's trig class, because this is also the first 5 minutes of my Calc 1 class, if you've ever been in there. The other instance where you probably saw this, and again, equally important, although not ever used in this class, the square root of -1. Can that be calculated? No. But what is it? What do we call a square root of -1?
I.
I. It's defined to be I. Based on that definition, then I can say the square root of -4, which equals the square root of 4 times the square root of -1, because it is a square root, and so it still has to obey the rules of roots. And this is equal to, not defined as, this is equal to 2i. It's equal to 2i as a result of this definition. So everybody here, when you defined I, you didn't calculate I, you said, we're going to call the square root of -1 I. And then from there, we're going to build all of the complex number system. Very important definition. But only the basic definition, it was necessary. You never said this, you never define things, you calculate them. Now these are results of your definitions. So in geometry, we always start with definitions, axioms, postulates, basic things, and then we eventually build up theorems. In this class, we do a lot of the same stuff. We start with basic definitions and basic truths. That's what an axiom and a postulate is. It's an absolute truth that cannot be proved because it's so basic. It's a starting point. So with that said, I'm going to define a Cartesian product. Now, the reason this is a little confusing is we use this symbol in this course for other things. Yikes. But the symbol also has a different meaning depending on the context. And by the way, I absolutely hate that we do this, but there are a lot of symbols that we will use that has a different meaning in the context. For example, we know I is the square root of -1, but anytime you ever did a summation, you don't worry about this. I've got the summation from I equal 1 to n of, I squared. I is an index. I is 1, I is 2, I is 3. I isn't the square root of -1. We use I as an index anytime we do a summation. Some of you, when you're doing vectors, you use I as a unit vector. Well, talk about confusing, because in linear algebra, you can have complex numbers in a vector. So you got to be really careful. In this context, we're defining it, but it also means, in most contexts in this class, it also means equivalent, which doesn't violate the definition part. I'm going to create ordered pairs, 1 alpha, 1 beta, 2 alpha, 2 beta, whoops, sorry, 3 alpha, 3 beta. The Cartesian product of A and B is the set of ordered pairs created by making the element of A the first coordinate and the element of B the second coordinate. This is the definition of a Cartesian product. Therefore, the entire XY plane in algebra is the Cartesian product of the real numbers and the real numbers. Now, those in linear algebra are familiar with the particular notation. And in Calc 3, I also use this notation. We don't typically use it before Calc 3, but we know if I said R, this is the set of real numbers. And the reason we use a script R is because a lot of times we like using a capital R to just capital R, capital S, capital T. Those might be my sets. And that's very confusing. We use a script R to represent the set of real numbers so that we're not going to misconstrue it. So if I said the Cartesian product of R and R, you're not going to list those. Why? Because there's infinitely many numbers. But what would I create here? I would create every possible ordered pair of real numbers, right? Positive, positive, negative, negative, 0, it doesn't matter. I would create every conceivable ordered pair. It doesn't every conceivable ordered pair, isn't that the entire XY plane? And in Calc 3 and in linear algebra, what do we call this? Anybody? We actually have a name for this. R2. We don't say R squared, we say R2. Oh, so in Calc 3, when we're in 3 dimensions, what do we call that? R3. But that turns out to be a 3-way Cartesian product. And I'm going to show you what that means, because the notation we use in calculus actually is exactly the same notation as we're using here. We just don't use the term Cartesian product. So what if we did, how about if I did the following, just for the heck of it? What if I said, I want to do B cross A cross B? And by the way, the parentheses here would matter. Now I'm considering this as an element. Well, it is an element. It's an element of A cross B. But now I'm going to be considering it the second coordinate. Oh boy, that's kind of weird. I'm not sure I have room to write them all down. So it's going to be alpha comma that. Alpha comma that. And eventually my last one would be beta comma, that was the last one. Okay, this would be B crossed with this. So now I'm considering every one of these as the second coordinate. This is very confusing notation, that's true. But wait a minute, in Calc 3, you know, I have an ordered triple. I have 1, 3, 5. I don't have parentheses within my parentheses. You're correct. These parentheses here meant that I was considering this as a second element, and this is a first element only. So in Calc 3, when I have ordered triples, in that case, in Calc 3, we would say R cross R cross R. That now means it's an ordered triple. Oh, so as I keep, no parentheses. I'm not saying I'm going to group these second ones, because then points would look like that. And this is called, of course, R3. So in linear algebra, when we're doing vector stuff, I'm guessing a lot of you have had linear algebra. In Calc 3, we deal in 3 dimensions primarily. In linear algebra, we deal in what's called n dimensions. There's no limits. We can do 2 dimensions, 2,000 dimensions. It doesn't affect anything. In that case, we call it Rn. So those are ordered n tuples. So if you haven't had linear, that sounds kind of scary. It's really not. We might talk about n dimensions, but most of our examples, we still do things in 3D just for the algebra, so it doesn't become too intense. So a Cartesian product, again, I'm taking the elements of the first set and they become the first coordinate. The elements of the second set become the second coordinate, and I write every conceivable way of matching them together. So in this case, the elements of the second coordinate were already ordered pairs. So I could now have another one crossed with this one, and this whole thing might be a coordinate. It gets crazy. I wouldn't worry too much about that. This is just, again, this is the introduction of a Cartesian product. A Cartesian product is very, very simple to work with, and we do use these often. So again, now when you think about algebra, okay, I did R cross R every time. Now, what if? What if you're not going to be dealing with real numbers, but you're going to be dealing with, let's say, integers, or more complicated stuff like complex numbers? So then what would we call that? Well, let's suppose I only wanted to deal with integers. So now what are the symbols? Because I want to make sure symbolically we're all on the same page. All right. So when we talk about the number sets in remedial algebra, we talk about the number sets. In linear algebra, we talk about them because we want to introduce the concepts of closure. Closure is the idea when I take 2 elements of a set and combine them using whatever operation I'm talking about. Usually that's addition or multiplication. Is the resulting value still in the set? That's what closure is represented by. That's linear algebra. That's not this class. But when we talk about the number sets, usually the lowest number set we refer to as n. That's the natural numbers. Okay, that's the 1, 2, 3, forever. If we throw in the number 0, we call that the whole numbers. So this is also the positive integers. This is then called the non-negative integers. So now when we want to talk about all positive or negative, so I would write like this, dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. That's the simplest way. Oh, this is called the set of integers. And up until maybe Calc 2, you always used a capital I. Never again. Anybody know what symbol we use for the integers now?
Z, I think.
Capital Z. Now, people say, why do we use a capital Z? I think we use a capital Z. It's kind of like the secret handshake. You see, when you're doing math and you use a capital Z, then I go, ah, yeah, they know. You know, they're a math person. They have more insight than those other guys who use capital I's. See, capital Z is like the little hint, the secret code word that says, hey, I know a little more math than you do. I have no idea why we switch variables. Everybody uses a capital I for integer all the way up until around now, and then now we change it to capital Z forevermore. I wasn't there. When the Universal Math Council got together and decided this, I don't know, I might have been in the bathroom or something. They said, we're going to use capital Z from now on. Therefore, this is also called capital Z plus. You're never going to use this symbol mathematically really ever again. You're going to use this symbol. This says the positive integers. That's the definition of the natural numbers. They are the positive integers. Why are they called the natural numbers? Well, basically, literally, they're the numbers that occur in nature. When I'm looking at the leaves fell off the tree and I'm counting how many leaves. I don't start with 0. I start like, I see 1 leaf, I see 2 leaves. But what if some of the leaves have been broken up? I still see 1 piece of a leaf. I see 2 pieces. I see 3 pieces. When you're starting to count things, you count using natural numbers. That's a lousy explanation. That's kind of where the term comes from. So that's Z plus. So Z minus would be everything this way. So that would be Z minus. Well, what if I'm using the 0? Well, then we call it the whole numbers. We don't want to get confused because Z plus does not use a 0. Z minus does not use a 0. Now, if I consider, and by the way, for this class, the most important set is the next set. If I consider every conceivable quotient of integers, whoops. Okay, this is the formal definition of the rational numbers. This is the most important number set in this class because this class is called discrete mathematics. Calculus is the mathematics of continuous functions. This is the mathematics of discrete functions. You say, what's the difference? Simple difference, okay? Between the numbers 0 and 1, how many numbers are there? In the interval from 0 to 1, anybody guess how many numbers are there between 0 and 1?
Are there like infinitely many numbers?
Yeah, I'm not going to ask you to list all of them, but yeah, there's infinitely many values between 0 and 1. Now, if I said, how many children do you have? Well, you could have 0, you could have 1, you could have 2. Are there any values between 0 and 1 when I ask you how many children you have? No. See, how many children you have would be a discrete count. Oh, I want to time you. I'm gonna flash a light and then you're gonna press a buzzer. As soon as I flash a light, you're gonna press a buzzer. And I'm gonna time you and see how long it takes. And let's say everybody in here, your reflexes are fast enough that you can all do it, within 1 second. That means everybody's time is going to be a time between 0 and 1. That's a continuous thing. All measurements, absolutely, all measurements are continuous. There is no such thing as a finite measurement. That's a contradiction of the term. Finite is what you approach, or excuse me, what you represent, what you write down. If I asked you how tall you are, and you said, I am 6 feet tall. Oh, okay. So that means down to the subelectronic particle, you're exactly 6 feet tall. No, actually, that would be mathematically impossible. That would be literally 1 out of infinity. No, it means to the nearest foot or even to the nearest inch. You might be 6 foot and a quarter. You might be 5'11" and 7/8, but you're going to say 6 feet. 6 feet would be a convenient representation of an infinite number of potential heights because it's a measurement. If I said, how much do you weigh? Nobody's going to give me a decimal answer, yet everybody should, because there's no possibility you weigh exactly a whole number of pounds. That's actually mathematically impossible because there are an infinite number of possible decimal representations. You're rounding it. So in a physics class or a chemistry class, when you're doing a measurement, you're going to report a finite value, a finite number of decimal places, because it's inconvenient to report more than that. But your measurement was automatically infinitely many decimals. A discrete value, I have a value, and then there's nothing in between. Most of the time, the values would be integer values. So if I said, how many units are you carrying? How many children do you have? How many houses have you lived in your lifetime? Think about this. They're going to be positive integers in all likelihood. I don't think anybody lived in a negative number of houses, or I lived in a half of a house. I don't know. So it's the set of all quotients where the two numbers involved are integers. They don't have to be positive, and the denominator is not 0. We do not consider undefined as being a rational number. Okay, undefined isn't a value at all. Undefined cannot be an answer when you say how many. Now, with that said, there's some confusion because aren't there decimal representations as well? Oh, now see, the next set of numbers are called the irrationals, and we generally use IR. And when I put these two together, I get what are called the reals. So the irrationals are essentially every real number that is not rational. But then how do you describe an irrational number? A number that can't be written as a quotient? Yeah, but that might be true, but that doesn't tell me anything. See, if I'm looking at a decimal value, I don't know if that can be written as a quotient or not. Not right away. So I'm going to give you the simplest definition from a decimal standpoint. And I do this in my lower level classes because it's necessary. So one thing you know about rational numbers, a rational number in terms of a decimal representation, and this is important in this class, and we will use this periodically, a rational number has two different possibilities for a decimal representation. See, 1/2, 1/3. What should I write? I don't have all day, so I don't think I want to write threes forever. Well, what should I probably write? Anybody?
3 with a line on top.
Yeah, what does the bar mean? It means I'm going to continue with threes forever. All rational numbers have one of two possibilities. They either have what's called a terminating decimal, or they have an infinite repeating sequence. Now, it doesn't have to be one number. It might be two numbers. It might be 5 numbers. It might be 10 numbers. But there's a repeating sequence. And by the way, the word sequence is important because the order of those numbers is everything. All rational numbers either have a terminating decimal or an infinite decimal where the sequence is repeated, exactly the same forever and ever and ever. So there's only one other possibility. And what is it? An infinite non-repeating sequence. So that is the definition of an irrational number. It's a number with an infinite non-repeating decimal sequence. Square root of 2, pi, e. These are examples of irrational numbers because you can write decimals forever and ever and ever. You're never going to repeat a sequence. Will you repeat decimals? Well, of course, because there's only 10 digits. Of course, you're going to repeat numbers. You're just never going to repeat the pattern. Okay, so if all real numbers are either rational or irrational, the irrational ones we tend not to spend time on in this class because they aren't good for the rules we're developing. We're going to work with essentially rational numbers because we're starting with discrete values. Discrete values are usually integer values. Okay, so that's a notation thing, but it's also a vocab thing, and I want everybody to be very comfortable. Now, there is one more set that we don't always talk about in this class, and that would be the imaginary numbers, which we usually use IM. Now, what's an imaginary number? Well, that's a real number times I. That means there's exactly the same number of imaginary numbers as there are real numbers because it's just times I. And when you put these two together, you get what's called the complex numbers, which we usually use as script C. We do not deal with the complex numbers in this class at all. Nope, none. Okay, they're not what we are interested in. You deal with those in other classes. At the very end of linear algebra, we introduce them. they're all the way through differential equations. And then when you get to upper division, if you do a course in complex analysis, that's basically the calculus of complex numbers. Okay, so that they have their important uses, but not for this class. But I just want you to be aware. So we don't even work with the reals all that often because we're not interested in the irrationals. We're interested in the behavior of rationals, and very, very particularly, what are the rules governing rational numbers? We're going to get into those later when we do the proofs. Okay, so this is the first lecture of the semester. So let me go ahead and stop recording now.